friction between two objects that are not moving. Absolutely. Looking for my lecture. Sorry. Do. Oh, I sneezed twice on my mask today, you guys. It's just that kind of day. Okay. What'd you say? Hi, everybody. All right. So, when we talk about our different types of friction, a couple of things that we want to make sure we remember. So we said static friction is the friction that exists between two objects that are in contact and are not moving. Okay, so that's static friction when they're not moving. Another thing is friction can only exist between objects that are in contact with each other. So you cannot have friction of an object that's like falling through the air. Instead, we're going to talk about drag, which is the other type of friction or other type of resistance force that you learned about in your reading last night. So kinetic friction is, of course, going to be the friction between two objects that are sliding against each other. And one of the things that we're going to talk about is how these two objects or how these two types of friction come about and what they actually mean. Okay, so if we zoom in as close as we possibly can on a surface, we're going to see that the two objects that are in contact, no matter how smooth they are still going to have what we call these jagged interactions. So unpredictable molecular interactions. If I keep zooming in and zooming in and zooming in, I'm at some point going to see that molecules are sliding against each other when they're moving, or if they're not moving, it could be because they are not evenly aligned. Okay, no matter how smooth the surfaces are, there's always going to be some level of this. Two scenarios in the crate pushing on the ground example. One of those scenarios is that no matter how much you push, it does not move. Okay, what that means is you have not put enough force behind the movement of this crate in order to get it to overcome that coefficient of static friction, which is one of our new pieces of terminology. As you increase the amount of force that you are pushing on that object, the amount of static friction also increases up to a certain point. Okay, so there's a maximum amount of friction that will exist between those two surfaces. Once you push hard enough, though, you can overcome that static friction force and you can get the object to start moving. At that point, kinetic friction takes over. Okay. Okay. Did I skip 2 force? Okay. So, that being said, you move in and in and in, right? Like we said, if we look at the molecular level, what we're going to see is that no matter what, there is always going to be that frictional force, and it will exist between those two objects. It's never going to be a smooth interaction. Okay, so just kind of remember that. The more force you apply, the more likely you are to be able to overcome the maximum amount of static friction that is already present, and then let kinetic friction take over. From there, we talk about our first equation of the chapter, which is the calculation of the force of static friction, F sub s. Remember that whenever we draw our free body diagrams and we put friction in them, we always use that lowercase f. In this case, we're going to have to indicate static and kinetic friction using the lowercase s and the lowercase k. Mu s is going to be a coefficient of friction, in this case static friction, because the s means static. The mu s is going to be a number without a unit, so it is unitless. That was one of probably your questions that you had on your reading. Unitless, meaning there is no number, there is no descriptor. N is going to be the normal force, okay? And so we have seen normal before. We know usually what our method is for calculating normal involves whatever the opposing weight force is of that object, okay? This is giving us a way to calculate our frictional force instead of just assuming it is a value in a scenario. Right? So now we're moving away from just me giving you the number to you calculating the number yourself. Okay? From there, we have to learn a few things about the difference between a friction force and its maximum friction force. Remember, we just talked about the scenario where the amount of friction an object experiences in the static dimension is going to be limited to a maximum amount. But up until that maximum amount, it will equal whatever the opposing push force is, right? So until we get the object to move, we have this changing amount of static friction, okay? Once we've gotten to the maximum amount of static friction, so Fs max is what we're talking about here, which again we're going to calculate using a static coefficient of friction and the normal force. Once we have this value, after this value, so any number past the maximum friction, static friction force is going to have to be converted into kinetic friction, okay? So once we get to the max, that's when the object can start moving. And once the object starts moving, we see that a different scenario takes hold. With our static and kinetic coefficients of friction, we're going to see something very interesting about the values. But before we do that, I just want to show you what the frictional force in the kinetic way would also, how that would be calculated. Similar thing, right? Exact same equation, except you're using a coefficient of kinetic friction and the normal force instead. So they are calculated the same way. With kinetic friction, the value does not change, okay? So the kinetic friction force is like a value that will always be the same as long as the object is in some sort of movement, okay? With our friction in the static dimension, it does change depending on the forces being applied. Okay, so let's look at some friction coefficient values. One thing you will notice is that the maximum coefficient of friction that was given in your reading is 1. Most of them are numbers below 1. Okay, that's the first thing to notice. They are numbers between 0 and 1. The next thing to notice, this is my static friction coefficients. These are my kinetic friction coefficients. What do you notice about the values? They're not the same. What else? What other observation can we make? The static is always larger. The static coefficient of friction always has a larger coefficient than the vice versa kinetic coefficient. Now, are there cases where they're very, very close? Yes. Are there cases where they might be identical? Yeah, a lot of like ice scenarios or like really, really smoothed up surfaces may have similar, but there are very few, I don't even think there are examples where kinetic is going to be bigger than the static, okay? So keep in mind, and this should make a little bit of sense based on what we've talked about, that friction force in the static direction is a big one you have to overcome. Once you got the object moving, though, things are already in motion. It has momentum, according to Newton's first law. Or inertia, if you will. Okay? All right, so next thing we want to look at is just kind of a very, very basic example. This one says, if the crate you were trying to push has a mass of 100 kilograms, the normal force would be equal and opposite if we're on a horizontal surface. Do you agree? Yeah. Do we agree? Raise your hand. We're thinking about a box that is moving on a surface that is horizontal. This is 100 kilograms. When we draw our free body diagram, we know the weight of this object would be equal to mass times gravity. We know the normal would point perpendicular to the weight force. So the weight and the normal on a horizontal surface should be equal to each other, especially if the object is not moving in the y direction. This will happen a lot. This will happen a lot in your equations. Where does this not happen? Think about something we worked on this week. On an angle! I like it. Ramps are going to have that unique situation of the weight vector pointing down and the normal vector pointing on the angle. So in other words, you need to know the perpendicular weight to figure out what the normal is in that particular scenario. You see how these two are going to be the ones you want. Friction always points opposite. Assume it's not moving down. Assume it's moving down the ramp. So now we can go back to our ramp scenario and we can try and figure out what the force of friction is given information that we now know. Okay? In this particular case, we're told 100 kilograms, so we're on our horizontal. So we know that the weight vector is going to be that 100 times 9.8. We know that the coefficient of friction for that particular scenario is given to be 0.45. So we're going to plug those numbers in, and we're going to get 440 newtons as the friction force, or the max friction force. So in other words, if we want this object to start moving, we have to put 441 newtons of force against that 440 newtons of static friction. Does that make sense? Okay. So if F applied is any number up to 440, then the friction will be whatever the opposite number is. So let's go through a few scenarios. Let's go through scenario A. We know we need 440 newtons at least to get this to move. If F applied is 275 newtons, what is the force of friction? 275 newtons. Okay? If F applied is 440 newtons, what is the static friction force? 440 newtons. If F applied is 500 newtons, your static friction no longer exists. It becomes the friction of kinetic. What we're saying is any value up to 440 newtons, that static friction can go ahead and be opposed, right? And they're going to be equal and opposite. Beyond this, we have to do a different calculation. We have to figure out what the coefficient of kinetic friction is, which we don't know because they just told us the static friction. And then we could calculate the same thing. Does that make sense? Okay. So we feel good about friction. We'll do some practice. Always practice. All right. And this one just kind of goes through and says, okay, so here's the friction in the kinetic direction. I didn't even know I had the second part of the problem. I'm so dumb. Okay. So this one says that if after we overcome that 440 newtons, here's what the new kinetic friction force is going to be. So we would take that number, multiply, and we'd get that the friction force in the kinetic is going to be smaller. So remember that this value will always be a smaller value than your friction max in the static dimension. Sorry. Okay? All right. So just some reminders. Coefficients are always going to be between 0 and 1. Those coefficients depend on what two surfaces you're talking about. So wood block on ice is going to have a different static and kinetic coefficient than a steel block on concrete. Wheels on road versus wheels on ice. That's a fun one. We will do that problem. Always good to remind you in the winter to drive slow. Okay, so lots of different examples of frictional surfaces and or interactions that are going to be pretty important. You can think joints in your sockets, so like in the human body. You can think how tissues in your body rub up against each other. So think like your lungs go in and out, right? There's a friction that goes on between your lungs and the outer tissues of your body. There has to be. Otherwise, there'd be no room for expansion and contraction. Okay? The heart muscle that is currently that moves, right? Any object that moves in your body has to have some kind of a frictional force that it's always working against. Now, what else do we also have in our body to make sure that those friction forces don't become too intense? Fluids. Fluids everywhere. Different fluids, types of fluids, fluids everywhere. Those fluids are all lubricants, right? So they're there to actually decrease that coefficient of friction and to make sure that your muscles and your tissues don't tear. Okay? Saliva, really useful for your mouth. If you didn't have saliva in your mouth, can you imagine? That would be awful. Walking on ice. Anybody done that lately? I was trying to take a walk with my husband last night, and I was like, I'm just going to walk in the street. rather get hit by a car than slip and die. Seriously. What other types of friction can you think of? Scenarios where you either have too much or too little.
Me sitting here. Is that friction? Like,
Where would the friction force between you and anything else be?
The chair.
Yep.
And the chair and the floor.
And the chair and the floor. Good. All right. Tires and cars are probably our most common example. It's really where we end up focusing a lot as people because we spend a lot of our lives in our cars, right? We do, unfortunately. Yes, good and bad. All right, so let's do a friction problem together. First thing is we're given information about the skier. We're given the mass of the skier. We're given the angle in the diagram. We're given the coefficient, or we're told to find the coefficient of kinetic friction. If we know the friction is 45 newtons. So here's my diagram. Well, I'm going to redraw my diagram. Always start with a what? We always start with a free body diagram. If you start with a picture and then that becomes a free body diagram, that's fine. I know he's not sliding, but you know what? Deal with it. Okay? Remember that weight vectors always point straight down. Since he is in contact with the surface, there is, of course, a normal. W perpendicular, W parallel. This would be friction. So here we are so far. How does this become a free body diagram? What do I do next? Rotate it. I like to rotate them, remember, so that normal's always pointing straight up. Our diagram becomes this. Does everybody see how it becomes this? All I did was put the components of the weight vector out there so that you saw them. The angle is given at 25 degrees. W. Cosine? Is it Jason? Yeah. Okay. So what do we need in order to figure out the kinetic coefficient of friction? What's the formula?
The UK.
So mu k, which is one variable. Remember, that's our coefficient. And then we need the normal. In this diagram, do you agree this?
Yes.
Okay. So one step further, do you agree that? Are we in agreement? Okay. Do we agree that?
Yeah.
With me so far?
Yeah.
Okay. Okay. So we were given mass is 62. So we need a normal force.
Wait, does it matter what mode you're in?
Yes? It's an angle.
Oh, yeah.
That angle's given in degrees, so you should be in degree mode. I got 550.67. Okay? So now we're moving up here. Now that we have the normal, we were given the friction the kinetic dimension is this. We don't know the coefficient. We were told to find the coefficient. And then we just calculated this guy. So what's our coefficient of kinetic friction? Remember that you can test whether or not you get this right by knowing that your value is supposed to be between 0 and 1. So what we get?
0.8. I got
45 over 550? Should not be 80%.
Yeah, no, I got that.
You got 0.08?
Yeah.
Oh, because I put 55.
All right, what's the unit?
There's unitless.
Trick question. There's no unit. Okay. All right, let's do some more. Let's do another one. We've got a mountain climber. She's holding on to this side of the rock pretty tightly. We've been given an angle. We have a applied force. Our goal is to find the tension in the rope and what force she must exert on the vertical rock to remain stationary. So there's got to be friction somewhere. Okay? So let's draw a diagram. Let's see if we can find it. Tension. F applied. You're gonna draw me an axes so that I can see. This is. That means this guy is 31 degrees. Alright, what am I missing in my free body diagram so far? Definitely friction. Let's wait on friction. Would there be a normal force? What do we think? I would guess yes. However, remember that it's always perpendicular to the surface that's in contact. So where should it point? Do you agree? Because her feet are in contact with the wall. So our axis is all kinds of screwed up. Okay, what else are we missing? All objects have weight. We're assuming that weight points straight down. Okay, what's a major assumption we can say here? Let's go F net and F net. Someone raise your hand and choose X or Y. Tell me what you think it should be. Should it be MA or 0? And tell me why. Raise your hand, raise your hand. Go ahead.
No, because I don't know.
So read the scenario and tell me what you think it should be. Go ahead, Aiden.
Is F not Y and A?
Why do you say that? Well, think about it. It does say something pretty important about her movement. Is she moving or is she not moving? She is not moving, so what should it be? When in doubt, 0.
Wow.
Okay? All right, next thing that is probably a problem for all of us in the room is that we have things on angles, don't we? We don't like angles. So what are we going to do? We're going to resolve them. Boys and girls?
Wow.
We're going to resolve them. We're just going to come up with things to say. Right? Like we're going to do like tension X and tension Y. We just want expressions. You're doing great. You guys are doing great. This one's kind of complicated. it's really okay.
It doesn't matter.
But it's really okay. Okay, so now let's do some more. What are you gonna do now? Oh, I guess I want to do this TX. And I want to do this T1Y. I want to do this triangle. Because my angle's here.
Too small
Okay,
to be
so
this
you
complicated.
My diagram is kind of complicated. Okay, so I'm going to start with tension. And I'm going to look at my triangle specifically. And then I'm going to make sure that I look at where it's oriented. Okay, so remember our orientation of our vectors have to be negative and positive. So for this guy, T1X should be what? Negative or positive? Negative. So I'm just going to put a negative up front. T1Y, positive or negative? Positive. Okay, now I'm going for expressions. I guess it's just TX and TY. There aren't multiple tensions, so I don't know why I do that. I just like default. Okay, so T. Help me with my triangles. Opposite, so sine of 31 degrees. And this one is positive T cosine of 31 degrees. Okay, now I'm going to do F applied. So this would be F applied. F applied. Both of them are positive because they're in the first quadrant. So this one is going to be in the X cosine. This is why I said you have to be very careful about your angles. You can't just assume that X is always one thing and Y is always one thing. Because look, the X up here is sine and the X down here is cosine. Right, so it does very much matter what quadrant you are in with your angles. Okay, now let's write our expressions. We know they're going to equal 0. Let's also redraw our free body diagram to represent all forces on the 4 axes. Okay? So up here, I have T in the Y. I've also got F applied Y. So those two are both Y's, right? Then we've got TX that points this way. We've got F applied X. And we've got normal. And down here, we have W. Now, not drawn to scale, right? Not all of my forces are not drawn to scale like they were in those diagrams you saw yesterday. Yes, ma'am. Okay. All right, so now I'm going to write out my expressions. Remember, everything to the right is positive, everything to the left is negative. I'm going to start with the X. So I've got F applied X plus N. Minus TX. Okay. This guy, I've got that. You guys are going to love this next step. You always do. I'm going to rewrite. I'm also going to do a couple of things. Do you agree that that's the same thing as what was up there? Okay, do we see how this became this? And this became this? And this is why I say you're not going to like the next step, and it's because we're going to plug all of these in to these. What's going to be cool is we're going to have 2 equations and 2 unknowns. Okay. F applied X was given Tx was given as negative T sine of 31 degrees. F applied y was FA sine 15 degrees. Ty was T cosine 30 degrees. M and G, we were told she's 52 kilograms and 9.8. Okay. This is exciting. All right. What do we know about normal? What do we typically set normal equal to? Does anybody remember? Can we do that here? Let's do it. See what happens. So this becomes this. What do we do next? How do you solve a system of equations with two unknowns? So we're going to solve one for one of the two variables. What are the two variables we need? T and FA, right? These are our two equations that we're going to use to do that process. Okay? So which one do we want to solve for one of the two variables? I think one of them is easier than the other. And I think it's that first one to solve for t. Does anybody else agree? Yeah, because all we have to do is divide both sides by negative sine of 31 degrees, right? Okay, so let's do that first. Can I erase these expressions so we understand where they came from? You have them in your notes. Can someone do me a favor and plug in 52 times 9.8? Okay, and then can someone do me a favor? Tell me what the sine of 31 degrees is in your calculator.
I thought it was gonna make a big noise.
Say again?
0.51.
Okay. Can someone tell me what the sine of 15 degrees is?
0.25.
Can someone tell me what the cosine of 15 degrees is?
0.96.
And then the cosine of 31.
0.85.
Okay. Why did I do that? Because numbers are just easier to deal with if we don't have to deal with the trig expressions. So hopefully this makes things just like a little bit more straightforward when you start rewriting it and trying to solve equations. Okay, so first things first, I'm going to divide both sides on this one by the 0.51, negative 0.51. So that's going to become that expression. Could I simplify this expression? Yeah, let's do it. So divide 0.96 by 0.51 for me.
Yeah, 1.88.
And then do 509.6 divided by 0.51. So there's my first expression for t. All right, what am I going to do with that? I'm going to plug it in down here into equation 2 as t. So this whole expression is going to go into this expression for t. Okay? Okay, here we go. Okay, so let's distribute the 0.85 into the expression. So multiply your 1.88 times 0.85. What? 1.88 times 0.85.
1.59.
Okay, and then do that 999 number times the 0.85. Don't drop your negatives, right? Watch your signs. Who missed algebra? Love algebra. Good time. Go ahead.
849.32.
All right, from there, it's a simplified algebraic problem. Solve that for FA. Give me a number. Sorry, it like froze on me. I apologize. What'd you get?
907.20.
Okay. All right, next one's going to be minimum coefficient between her shoes and the cliff if she's not moving. So it's part of the climber's weight is supported by her rope and part by friction between her feet and the rock face. So how are we going to calculate that coefficient of friction? I'm so sorry. It's all good. They can see part of what I'm doing, so they don't need to see the. Okay. Every single one of my plugins is like 5,000. So how are you going to calculate minimum coefficient of friction? Minimum coefficient of friction being mu s. We're just gonna say. What information do we need? We need the equation. So what's the equation? Don't we already have the normal? Didn't we say we were assuming it was the same as weight?
Yeah.
So can we calculate this?
Yeah.
Are you sure?
Wait, no, we don't have US and FS.
We don't have our friction in this particular case. So we're going to have to talk about it tomorrow. I'm sorry. I won't be here tomorrow either. I will film a video for you to watch. Please bring your headphones. Okay? It is a cliffhanger.
Literally.
Oh
my gosh.
Oh, literally a cliffhanger.
I like made a joke without
Guys,
it meaning
that was not
a joke.
me. That was Lilia.
Good job.
I'm so proud of you. All right, guys. We'll see you tomorrow.